So remember when we used the equilibrium expression, but we plugged in the initial concentrations instead of the equilibrium concentrations, that told us which way the reaction would shift to reach equilibrium. And that was called the reaction quotient, or the Q. So for KSP we have the same thing, but we call it the ion product. So again, we're just taking the equilibrium expression and then plugging in the initial concentrations of the ions instead of their equilibrium concentrations. So if the ion product Q is larger than the KSP value, that means there are too many products, which are the ions, so the equilibrium will shift to the left. The ions will combine to form the solid, and this is called precipitation. And if the Q is less than the KSP, then there are too little ions, so the solid will dissolve more. The equilibrium shifts to the right. So here we have a situation in which we have 150 milliliters of 0.01 molar magnesium nitrate and 250 milliliters of 0.1 molar sodium fluoride, and they're mixed together in a solution. And so in this problem, unlike the previous problems, before we had a solid that we put in the solution and we want to find how much it will dissolve. Well, here we start with the ions and we want to find how much solid will form, and then that solid then dissolves a little to produce the ions again. So basically we want to see if a solid will precipitate out of this solution of ions. So we know sodium and the nitrate, any compound with those two will always be soluble. So you can basically ignore the nitrate and the sodium ions. But what can happen is the magnesium and the fluorine can combine, because magnesium fluoride is insoluble. And here's the KSP value for magnesium fluoride. So we want to see if magnesium fluoride will precipitate when we mix these two solutions. And to do that, we can do the ion product, the Q. So first we need to find the new concentrations of the magnesium and the fluorine ion. Because see, when we mix these two solutions, the total volume changes, while the moles of each substance stay constant. So their concentrations will change. So we're going to use the millimole since we have the milliliters. So the total millimoles of magnesium is just 150 milliliters times its concentration. And then the millimoles divided by the new volume, which is 400 milliliters, because you just add the volumes of these two solutions. And then that gets you the new concentration. And we did the same thing to find the new concentration of the fluorine ion. So once we have those, we can plug them into the ion product and calculate the Q. And we find that the Q is greater than the KSP, which means the equilibrium will shift to the left, because there are too many ions, so they will form the solid. So we know that the magnesium and the fluorine will precipitate as magnesium fluoride. So now we need to do a stoichiometry problem, because we can assume that this reaction, the magnesium and the fluorine combining to form magnesium fluoride, we can assume that this reaction is going to completion. So we have the single arrow instead of the double arrow. And we can assume this because we know that the KSP value for magnesium fluoride is very small. So at equilibrium, there will be mostly magnesium fluoride as a solid instead of in the ions. So we know after all this is done, there will be very little of these ions left in the solution. So to simplify the calculation, we just assume that this reaction goes to completion. So since it's the stoichiometry problem, we use the moles of each substance, not the concentrations. So again, we have 1.5 millimoles of magnesium and 25 millimoles of fluorine. So obviously, the magnesium is the limiting reactant, so it will lose 1.5 millimoles, and then fluorine will lose 3 millimoles, since it's in a 1 to 2 molar ratio. So all the magnesium ion is used up, and we have 22 millimoles of fluorine left in the solution after the precipitation occurs. So now that the precipitation has occurred, we want to do another equilibrium problem to see how much this magnesium fluoride, which was just formed from these ions, will then dissolve again. Because we know that the concentration of magnesium at equilibrium cannot be zero. It will be very close to zero, but it is not zero. So first thing, we convert the excess fluorine into the concentration. So we have 22 millimoles left over the total volume to find the concentration. And then to find the magnesium concentration, we do the equilibrium problem with the dissolving of magnesium fluoride. So we write the KSB expression, and if you do the ice chart, magnesium will be plus X, and fluorine will be its initial concentration plus 2X, because it's in a 1 to 2 ratio. So using the 5% rule to ignore this 2X, we can solve for X, which will be the concentration of magnesium, and also the solubility of magnesium fluoride. So in the next problem, we have a solution containing two different metal ions, and we're going to gradually add some iodine ions into the solution with copper and lead, and we want to find out which solid will precipitate out first, because copper iodide and lead iodide are both insoluble, so they can both precipitate out of this solution, but we want to know which one will go first. So to do that, we use the equilibrium expressions. So write out the equilibrium expression for the dissolving of lead iodide. We get this. And then we know the concentration of the lead ion. So we plug that in, and we can solve for the concentration of iodine ion. And what this tells us is when the concentration of iodine is equal to this amount, then this lead iodide will be in equilibrium. Because, if we plug in this concentration for iodine and this concentration for lead, it fits the KSP value. So this solution is saturated with lead iodide. However, once the concentration of iodine increases over this amount, then now the right side of the expression is too large. So the precipitation of lead iodide will start once there's more iodine than this. So we can do the same thing for copper iodide. We write out the equilibrium expression, plug in our initial concentration of the copper ion, and then solve for the concentration of iodine that will satisfy this equilibrium. So at this concentration of iodine ion, the solution will be saturated with copper iodide. And once the concentration increases over this amount, copper iodide will start to precipitate. So we look at these two amounts for the needed amount of iodine ion. So comparing these, we see that this number is smaller. So the copper iodide needs a smaller concentration of iodine ion in order to start precipitation, which means it will precipitate first. So as we add the iodine ions, when the concentration of iodine gets to this amount, copper iodine will precipitate, and it will precipitate until no more copper ion is left in the solution. And then after that, after the copper iodine is done precipitating, then once the concentration of iodine gets to this amount, lead iodine will precipitate.